Okay, students, let's go ahead and talk about the atomic structure. This will be strand 1 and standard 1.1. To begin, we need to talk about some ancient chemists. Okay, these technically were not chemists, as they were Greek philosophers, but they did get the ball rolling, so to speak, on the development of the atomic model. On the left here, we have Democritus, and he stated that matter is made of atoms that are indivisible and indestructible. Aristotle was also a Greek philosopher, and he stated that 4 elements are earth, air, fire, and water. Okay, there's a video up here that I suggest you watch on your own time. I won't make you do it here. You can pause this video and open the notes and watch that video, and it will speak more about the contributions from Democritus and Aristotle. John Dalton is our next scientist we'll learn about. He was alive during this time period here, and he stated that atoms of the same element are identical, which is a very important thing to realize in chemistry. He also stated that atoms of different elements can be mixed or combined in whole number ratios. So to illustrate that point, let's talk about 2 examples, and hopefully it will make more sense what he means by whole number ratios. So down here we have 2 hydrogen molecules, each containing 2 hydrogen atoms, for a total of 4 hydrogen atoms. We also have 1 oxygen molecule, which is O2, so there are 2 oxygen atoms, and they combine at a ratio that creates water. So we have 1, 2, 3, and 4 of these hydrogen atoms, and 1, 2. This is an important principle that we're going to talk more about this year, called the law of conservation of mass. But here it's going to show that whole number ratios are necessary, and we can't combine things in fractions. Okay, you can't have 0.6 oxygen atoms, for example. Likewise, down here, we have 1, 2 hydrogen atoms within this hydrogen molecule, and we have 1, 2 oxygen atoms within this oxygen molecule. They combine to form what is known as hydrogen peroxide, which has this formula, H2O2. Many of you probably have this in your cupboards in your bathroom or in your kitchen, and it has 1, 2 hydrogen atoms and 1, 2 oxygen atoms. Again, they can be combined or mixed in whole number ratios only. That's John Dalton. And J.J. Thomson is our next scientist. He was alive during this time period here, and he's famous for the cathode ray tube experiment, which led to the discovery of the electron. I suggest you watch this video, pause this video, open that one up in the notes, and you'll see an explanation of how J.J. Thomson up here was able to use this device to find the first subatomic particle known as the electron. Okay, subatomic means that it implies that it's below the atomic level. And we know that there are 3 subatomic particles. There's the electron, proton, and neutron. Okay, so from this experiment, the plum pudding model was developed, and it has an analogy with plum pudding, or something more familiar to us in the United States would be fruitcake, right? During Christmas, we sometimes see fruitcake pop up, and it has little pieces of fruit. It's very dense with cake and fruit, and these pieces of fruit are represented here as electrons. The cake part of this plum pudding, or this fruitcake, would be the positively charged portion, and it's sort of a cake-like substance of positive charge. Okay, this is the point at which I would like you to go ahead and do this Rutherford scattering simulation. It's meant to be an investigation into the next scientist and show how the atomic model was developed further from J.J. Thomson's plum pudding model. So I'll give you time to do that. Pause this video and give it a shot, and then restart this video and we'll pick up from there. Now that you've completed that simulation, hopefully, you can see Ernest Rutherford's gold foil experiment here. Ernest Rutherford was alive during this time, and he's known for the gold foil experiment, which states that atoms are mostly empty space. Okay, this is a great video right here as well. If you want to go ahead and watch that, it will show you a model of this experiment. It doesn't have any audio, but if you follow along, it's a very good visual. I'll go ahead and explain it here. What we have here is a lead shield, okay, this box, with some source of atomic radiation. This will be alpha particles, which are positively charged. That's important. And they pass through this screen and come into contact with this gold foil. It's just a thin sheet of gold atoms. Most of the alpha particles pass right through and are detected on the other side of this gold foil on this detector shield. Okay, some of them ricochet off or are deflected. Okay, they're scattered, some of which are scattered right backwards, and the ratio of how many are detected over here versus throughout the rest of the shield implies that most of the space on this gold foil is just empty space at this very, very tiny level. Okay, the nucleus is very dense and positively charged. That comes from the idea that not very many of these alpha particles hit something and were deflected. So that means that the nucleus is very small relative to the size of the atom, and that it is positively charged because it reflects or scatters other positively charged particles. Okay, so that is, in a nutshell, the gold foil experiment. Again, if you did that simulation and watched this video, it should make more sense. The next scientist we need to talk about is Niels Bohr, and he developed the Bohr model of the atom, which proposes that electrons move around in circular paths, called orbits or shells. Okay, we're going to assume those are the same thing in this class, around the nucleus. The valence shell is the outermost shell, and that is an important thing, very important thing to remember later on. So let's go ahead and talk about what this model shows. Niels Bohr proposed that electrons are not scattered throughout the atom in the cake-like substance, but rather they orbit around the nucleus, sort of like planets. Okay, let's look at this sulfur atom, for example. Sulfur has 16 protons, as we know from the atomic number. In a neutral atom, it has 16 electrons as well. Okay, so we need to account for all 16 of these electrons outside of the nucleus. In the first shell, there can be two. There can be 2 electrons in the first shell, and they're both accounted for. In the second shell, there can be 8, and as we see here, all 8 of those are accounted for. In the third shell, we need to get to 16. So 1, 2, 3, 4, 5, and 6. And with these 3 orbits or shells, or rings, however you want to refer to them, we have our 16 electrons. Okay. Soon we will talk about the periodic table of the elements and see how it's organized in relation to these shells. But for now, I want you to understand that Niels Bohr came up with this model of the atom, and it was a development upon previous ones. And lastly, here we have Schrödinger, Einstein, Heisenberg, and other modern chemists and physicists that came up with the modern cloud theory of the atom. I won't go into this in detail because you have an assessment which asks you to do some research on each of these and show what you've learned. But basically, they said that electrons act as both waves and particles simultaneously, which is sort of a strange idea. And that led to the quantum mechanical model of the atom. Okay, again, I'll let you do more research on each of these, but basically, instead of orbits, really distinct orbits, right, we have more of a cloud. And this is the electron cloud model. And it has to do with probability. Okay, electrons existing as particles and as waves. It's a strange idea, but you can do some more research on that with assessment 1.1. All right. For now, I want you to understand that the atomic model it wasn't made all at once. It was the contributions of many scientists and physicists over centuries that led us to what we know about the atom today. Okay, so we'll pick up from here next time. Thanks for watching.